operating point is basically found in the transistor output characteristic. So to talk about operating point, we should have the transistor output characteristics, right? So first let me draw typical transistor output characteristics. Okay, the transistor output characteristics can be obtained from the data sheet. Okay, so it is mentioned in the data sheet. So for this, we will consider common emitter configuration. So output characteristics is nothing but information of variation of collector current with respect to variation of collector to emitter voltage. Since we are talking about transistor output characteristics, you have to pick output current and output voltage. Okay, if you roll back to common emitter configuration, you would find that the transistor output voltage is VCE and the transistor output current is IC. That's why along y-axis you have IC and along x-axis you have VCE. And this transistor output characteristics is plotted for different base currents. So this is the typical shape of the transistor output characteristics. So let's say this is, let me slightly extend the x-axis so that I can explain you with better clarity. So let us consider the first base current as IB0, IB1, IB2, IB3 and IB4. So it is plotted for different base currents. Set a particular base current, keep on varying the VCE and note down IC variation. Likewise, you now change the base current to a slightly higher value, say IB1, and then you start increasing the transistor voltage, and that is the output voltage, and start noting down the output current. So, for different values of the input parameter, that is base current, you can plot a family of curves. Okay, and remember, the magnitude of IB4 is greater than IB3, greater than IB2, greater than IB1, greater than IB0. Okay, so this is the comparison between different base currents. Okay, and then after plotting the transistor output characteristics, you are supposed to draw something known as load line. So load line will have two extreme points. Okay, how exactly we construct load line? Let me talk about it in the exact transistor biasing network. Okay, now just to explain operating point, you need not get into those details. So load line is basically a straight line drawn on the transistor output characteristics by joining something known as y-intercept and x-intercept. Okay, so when we carry out the load line analysis, you would find that this y-intercept or point y corresponds to something known as IC saturation value. Okay, so this y-intercept is nothing but IC saturation, which is nothing but the maximum collector current, and on the other hand, the point which is located at x position is called as VCE saturation, and this VCE saturation, which is nothing but the maximum collector to emitter voltage, which is equal to the power supply voltage VCC, where VCC is the power supply voltage. Let me write it here. VCC is equal to power supply voltage. Okay. Now, when you join the 2 points x and y using a straight line, what you get is a different intersection point with the transistor output characteristics. For example, the yellow line, which is called as the load line, intersects the transistor output characteristic, corresponds to IB4, and it also cuts IB3 characteristic curve, IB2 as well, IB1 as well, IB not as well, right? So basically, you get different operating points. Why operating points? Because if you, let's say for example, if you look at this particular operating point, let us call it as Q1. Just to give an example, Q1. So what are the coordinates of Q1? You have some x coordinate, and at y-axis you will also have some y coordinate. So x coordinate, we can write it as VCE Q1. You understand? Since it is found along VCE axis, let us mark the x coordinate as VCE Q1. Q1 for operating point 1. And similarly, along y-axis, we get the y coordinate as ICQ1. Okay. So in the beginning, what did I mention? Operating point is nothing but voltage and current value. Okay. So x comma y. So what is your x in this particular example? In this particular example, x is VCE Q1 and y is ICQ. So what we have done is we have identified an operating point at the center of the load line, and that operating point we have considered as Q1. So whenever you want to operate the transistor in the active region, okay, or whenever you want to operate a transistor as an amplifier, we must select a Q point which is located at the center of the load line. So Q1 points to amplifier operation. And how to get this point Q1? So Q1 you need to get by properly designing a biasing circuit. And how do you design a biasing circuit? By properly choosing the resistors and power supply voltage. So by properly designing a biasing circuit, one can fix the Q point either at the center of the load line or far away from the center point. For example, if you want the transistor to operate in the switching region, so you must place the Q point very close to y-axis as well as very close to x-axis. Okay, let us mark those 2 points using blue color. So this point, let us say Q2. All right. And the one which is located very close to the y-axis, let us consider it as Q3. All right. Now, the region which is closer to y-axis is called as, the region which is very closer to y-axis is called as saturation region. Saturation region. The visibility is poor with the purple color, so I'll use white color itself. So this is your saturation region. Okay, so saturation region is your the region which is found very closer to the y-axis, this hashed region. On the other hand, you can also find a region which is very close to the x-axis as well as, so that is this region. So this particular region is called as cutoff region. Cutoff region. We have 3 regions now. A region very closer to the y-axis, which we have termed as saturation region. And we also have a region which is closer to the x-axis, which we have termed as cutoff region. And we also have a region which is lying at the center of the load line. For example, this region. So this region is called as active region. Active region. So in the active region, in this region, so from Q2 to Q3, the region which is found between Q2 operating point and Q3 operating point is called as active region, where any Q point if you select, it is found approximately at the center of the load line. On the other hand, if you select, the Q point which is closer to saturation region, you would see that the current value is very, very high. So let us say Q2 collector current, we'll take it as IC2. Okay, and the corresponding voltage, if you see, what do you get? You get VCE Q2. So this is, write IC Q2. Okay, so corresponding to Q1, you have obtained point X and point Y. Point X corresponds to VCE Q2, right? And point Y corresponds to IC Q2. Now, if you carefully compare the value of IC Q2 with IC saturation, what do you find? You find that IC Q2 is very close to IC saturation, right? So you can say that the current which is corresponding to operating point Q2 is approximately equals to IC saturation. So here you can write IC Q2 is approximately equals to IC saturation. And what is IC saturation? The maximum collector current. Okay. On the other hand, if you look at VCE Q2, right? So where do you find? Not equal sign, approximate. If you look at VCE Q2, where this VCQ2 is located? VCQ2 is located very closer to the origin. And what is the origin value? 0. So this VCQ2 you can approximately consider as 0 volt. So this condition is analogous to short circuit condition. Current. In case of short circuit condition, current is maximum, voltage is 0. So if you design your biasing circuit in such a way that if you end up in fixing the Q point Q2, you would get short circuit operation. Short circuit operation. So this is also considered as closed switch operation. Right. On the other hand, if you select point Q3, okay, so if you were to extract the coordinates of Q3, you have VCEQ over here, and then you also have ICQ3 along the y-axis. So if you concentrate on the coordinates of point Q3, you would find that the current coordinate, right, or the current point which is located very closer to the origin, right? So this ICQ3 is approximately 0 you can consider, right? Why? Because it is located very closer to the origin. On the other hand, if you look at the voltage coordinate is located very closer to VC saturation, and VC saturation is VC saturation is equal to VCC. So current is 0, voltage is maximum. So which condition it mimics? It mimics the open circuit condition or open switch condition. So if you fix the Q point at Q3, you would expect the transistor to operate as an open. So as I mentioned, open switch is analogous to 0 collector current and maximum voltage. So current is 0 approximately and voltage is maximum approximately. Similarly, short circuit operation is analogous to maximum current, which is IC saturation, and 0 voltage is VC saturation. So this is called as the transistor operation or concept of operating point. So just to summarize, what we have learned today is that in order to find or in order to fix an operating point, a designer must properly design a biasing circuit. If your target is to design an amplifier, then you must fix the Q point at the center of the load line. Okay. On the other hand, if you want to design a transistor as a switch, then you should operate the transistor you should operate the transistor in the saturation region for closed switch operation, or you must operate the transistor in cutoff region for open switch operation. So switching operation is possible if you operate the transistor in saturation region and cutoff region, and amplifier operation is possible if you operate the transistor in the active region. Now let us study about different biasing circuits. So the first biasing circuit what we are going to discuss is an emitter bias. In the biasing circuit discussion, so what we will do is first we'll draw the circuit diagram and then we'll carry out the analysis. So when we carry out the analysis, a separate analysis is done on the input circuit as well as on the output circuit. Alright, so first let us write the circuit diagram. In our entire discussion, we are going to consider common emitter configuration, collector terminal, base terminal. As I mentioned, that biasing is a process of establishing required currents and voltages by connecting external resistors and power sources, right? So we are going to connect a resistor at the collector side, which is called as collector resistor RC. We are going to place one resistor on the input side, which is called as the base resistor. And we are also going to place a resistor at the emitter side, which is called as the emitter resistor, and place the power source VCC and a power source on the output side. Okay, basically it's a single power source whose positive terminal is connected to collector terminal as well as collector as in one end of the resistor RC and one end of the resistor RB. So this is your emitter bias. Okay. So after writing down the circuit, you have to mention the voltage levels, the transistor voltage levels. For example, the voltage which is measured between base and emitter terminal is considered as VB with the polarity upper side positive, lower side negative, assuming base is at higher potential compared to the emitter terminal, right? And similarly on the output side, you have a terminal voltage between collector and emitter, right? So that we will consider it as VC, upper side positive, lower side negative. Okay, so fine. So voltages you have marked. Now let us mark the currents. Okay, so the input current along the direction of power supply, the output current IC. Again, this current direction agrees with the power supply polarity. This is IC. Alright. So now we'll have to analyze this particular circuit. Okay. And since it is operating in common emitter configuration, let us consider the transistor current gain as beta. So beta is nothing but the transistor current gain. So next comes the analysis. Okay, so first let us do the input circuit analysis followed by the output circuit analysis. So input circuit. Okay, so as I mentioned previously that input circuit can also be called as base emitter loop. Okay, so BE loop. BE loop. So in the input circuit, as you can see, the base current is flowing in clockwise direction, right? So basically you can apply KVL in the direction of the power supply polarity. All right. Yeah, we have to mark the emitter current as well. We did not mark it. IA. All right. So let's apply KVL in the clockwise direction. CWD, apply KVL in clockwise direction. So let us start from the power supply. So clockwise means going up, then right, and then taking a circular motion, right? So minus to plus VCC. Okay, and then you have a resistor. Through this resistor, current IB flows. So there is a potential drop. Potential drop is IB into RB, and then coming down, so you're going to trace VBE. So VBE traced from positive to negative terminal, so minus VBE, right? And then there is a potential drop across resistor RE, which is nothing but IE into RE. So potential drop is minus IE RE, and there's no element in this path, so this is equal to 0, right? Now, as I mentioned previously, that on the input side, the input current is IB, and in the expression, the KVL expression gives two currents, right? IB as well as IE. You don't want IE in the equation, right? Because you want the equation to be expressed in the input current. So what you can do is you can substitute in place of IE something like IC plus IB, right? You can substitute in place of IE, IC plus IB, and you can also make use of the current gain relation, which is beta is equal to output current. Output current is collector current and input current is base current. So this implies that your collector current you can find using cross multiplication. So collector current is beta times IB. So IC is equal to IB into beta, right? So basically what you can do is in place of IE, you can substitute IC plus IB. And in place of IC, you can substitute beta times. So let's do that. So therefore, complete expression, therefore, we have VCC minus IVRB minus VBE minus IE into RE. So in place of IE, you see what I'm writing. I'm writing IE as IB plus IC. And what did we get IC as? Beta times IB into RE is equal to 0. Now you can open up the brackets and you can, keep IB as the common word, common letter, common term. So VCC minus VBE minus IB. I'll keep it out. So it is RB plus IB into RE plus beta into IB into RE. So what you can do is you can keep RE outside the bracket. So within the bracket you are left with 1 plus beta times RE and whole multiplied with IB is equal to 0. Right. So if you are still wondering how did I simplify, I'm just showing this particular simplification. So it is IBRE plus beta into IB into R. Right. So that I have shown here. So here IB, you can keep it out. So we have kept out. And then you have RE and then beta into RE. So you can keep RE outside the bracket. So within the bracket, you are left with 1 plus beta. Okay, so this is your simplified KVL. So you have on one side voltage and one side current, and therefore you can find the expression for input current, which is the base current. So as per Ohm's law, what is I? I is equal to V by R. So you have difference in potential, that is VCC minus VB, divided by the total resistance information. So that is RB plus 1 plus beta times I. Okay, so that's your input current. Very, in a very simple manner, you can find the expression for IB. Once IB is known, you can find the quiescent value or the Q value of collector current, IC, which is nothing but ICQ. And this IB can also be considered as IBQ. IBQ, IB, it's one and the same, don't worry. So IC is equal to ICQ is equal to beta times IB. Right, IB you have already calculated. Just multiply IB with beta, that will give you the collector current IC, which can also be considered as ICQ. So that's your input circuit analysis or base emitter loop analysis. So moving forward, let us consider the output circuit. Right, so next you write, apply KVL, output circuit. What do you mean by output circuit? Collector, emitter. Okay, let us revisit the collector emitter loop. Okay, so this is your output circuit, collector emitter loop. So over there you have to apply KVL. So while applying KVL, what I will do, I'll take the help of the power supply voltage. So power supply voltage is in this direction. So let us assume the KVL in the counterclockwise direction. Okay, so let us apply KVL along the direction of VCC polarity, that is basically you're tracing counterclockwise direction. You can follow the circuit. So collector resistor drop is minus IC into RC, and then you have collector to emitter voltage, and then coming down you have emitter resistor. So across emitter resistor there is emitter voltage drop, which is IE into RE is equal to 0. Now this is your output KVL equation. So even in this KVL equation you would see that there are two currents, IC and IE, and we consider output current as the collector current. So we don't want these two currents to be there in the output equation. So what you can do is you can make use of transistor current equation, which is IE is equal to IC plus IB. And now you can compare the collector and base current levels. So your collector current normally found in the range of millis of amperes, and your base current is found in the range of micros of amperes. So when you compare a milliampere current with microampere current, you can say that this IC is very much greater compared to IB. On that note, what you can do is you can write IE approximately equals to IC, right? So with that approximation, you will be able to maintain one single current in the transistor output circuit. So taking that into consideration, your KVL gets the following shape: VCC minus VCE minus, in place of IE you can write IC, and therefore you have minus ICRC minus IC into RE. So what we have done, in place of IE we have substituted IC, and therefore your collector to emitter voltage, right? So collector to emitter voltage VCE, which which can also be considered as VCEQ is equal to VCC minus the drop. So you have ICRC minus IC into RE. So you can keep IC as the common factor, then sum of the total output resistance. Sorry, that's not equal. So sorry. Yeah. So this is the expression for voltage. So LHS is VC and RHS is VCC minus this. So that gives the Q point. So you have found ICQ. You have also found VCQ. So ICQ is your y coordinate and VCQ is your x coordinate. So once you locate x and y, coordinate, you can say that you have identified the Q point. And if your Q point is found at the center of the load line, you can say that the given biasing circuit is meant for an amplifier operation. And if the Q point is, located very closer to the y-axis, or if it is located very closer to the x-axis, then you can say that it is not meant for amplifier operation and it is ideally suited for switching operation. So once you identify the Q point, then you can go to something known as load line analysis. So load line analysis, to some extent I have given a brief introduction while explaining the operating point concept, right? So this load line analysis is done on the transistor output characteristics. Okay, so output characteristics can be extracted from the transistor data sheet, and you transfer the contents of data sheets into a graph sheet, and then you find the operating point, and then you draw the load line. Okay, so let us not worry about the transistor output characteristics. Okay, now in order to draw the load line, right, we must have transistor output characteristics. And what are the coordinates of, parameters of output circuit? Output current, which is IC, and output voltage, which is VC. Okay. So since we are dealing with transistor output characteristics, you need not worry about the input KVL equation. You need to just consider the output KVL equation. So let us revisit the output circuit as in rewrite the transistor output equation. So what did you get the transistor output equation as? VCC minus VCE minus IC into RC plus RE. So if you examine closely, you have the X parameter as well as Y parameter in this transistor output equation. So if you look at this VCE, so where have you projected your VCE? You have projected VCE along X axis, right? So this is your X coordinate, right? I mean X variable, you could say. And then you have this IC, and IC is found along Y axis, right? So in order to draw the load line, you need to consider the x-intercept or extreme x point and y-intercept or extreme y point. So for that, what we have to do is, in classical math, what we do is we substitute x value as 0 and we find y value. And for the second iteration, we substitute y value as 0 and we will find the x value. But in electrical terms, assuming 0 is attributed to, short circuit and open circuit situation. Let us say IC is equal to 0. Let us say there are two variables, right? IC is also a variable, VC is also a variable. So in order to find the x-intercept or y-intercept, you have to assume one variable as 0. So assuming IC is equal to 0, right? So IC is equal to 0 is in electrical or electronics, field. The meaning of IC is equal to 0 is analogous to open circuit situation. Okay. Open circuit. So in electronics, the extreme conditions are either open circuit or closed circuit, and then comes the intermediate operation, which is called as the amplifier operation. So what if you were to you know create an open circuit situation in the given particular circuit? If open circuit situation, if you assume that is as good as you are considering the current is equal to zero, because in an open circuit current value becomes zero. So if you take IC is equal to zero, your equation takes the following shape: VCC minus VCE minus 0 is equal to 0, because IC you have assumed 0, so 0 into resistance value gives 0 volts. So you get VCE is equal to VCC. Now you remember, while handling the operating point concept, the x-intercept, we have assumed it as VCC. Okay, since VCC is the maximum power supply voltage, so this is called as VCE sat or VCE saturation. So this is your x-intercept. Basically, this point corresponds to x-intercept. So you have located the extreme x point, which is located at VCC, right? So along x-axis, you basically project the voltage, right? Say 2 volts, 4 volts, 6, 8, 10, 12, so on and so forth. And finally, you will locate the power supply voltage. So that's your VCE saturation point, and VCE saturation is equal to VCC. All right, fine. So similarly, you can now find IC saturation. So now what you do, you have assumed the open circuit scenario, right? Now you assume short circuit scenario, so which is analogous to putting VC is equal to 0. VC is equal to 0. So voltage becomes 0 when there is a dead short circuit, right? So this is analogous to short circuit situation in which current is maximum but voltage is 0. So if you assume VC is equal to 0, then your output KVL equation will have only the power supply term, which is VCC, followed by VCE, which we have assumed 0. You are left with IC into RC plus RE is equal to 0, right? And then you can find IC, so which is essentially the Ohm's law. I is equal to V by R. So it is VCC by RC plus RE. So the ratio VCC by RC plus RE basically gives IC, and this IC is the maximum current or the short circuit current, which is called as IC sat or IC saturation. IC saturation. Okay. And this point, IC saturation, we can consider it as our Y intercept. So let's bring down the characteristics. So you have located the Y point, right? And where is the Y point? Somewhere over here. And this point corresponds to IC saturation. Once you have IC saturation point and VC saturation point, what you can do? Using a scale, you can just join the 2 points. So basically, you will get a straight line. Okay, and the slope of this straight line is minus 1 by RC plus RE. The slope of this straight line is minus 1 by RC by RE. Why negative? Decreasing ramp it is traced as. That's why the slope Y is equal to mx plus c, right? And what's your output equation? Output equation is VCC minus VCE minus IC into RC plus RE equal to 0. Right, so what you have to do is you have to separate out x and y terms. So yeah, this is your current, right? So this current term has some Y information in the form of IC. This is your voltage term in which VC basically gives the X information, right? So let us, readjusting the terms in this particular equation leads to, say, IC into RC plus RE is equal to VCC minus VCE. Right, or IC is equal to minus 1 by RC plus RE into VCE plus 1 by RC plus RE into VCC. Okay. Now you compare the standard equation of a straight line with the modified output equation. In place of Y, we have IC. So Y is equal to, okay, so this is VCE, I'm so sorry. This term is VCE, okay, VCE. And then you have mx, right? So m stands for slope, and this entire term, this term stands for m, okay, m. So minus sign is present here, and that's the indication that the slope is a kind of downgoing ramp, right? And then you have VCE. So what is VCE? VCE is your x variable, right? Along x-axis you have projected VCE. And C is a constant, so this is your constant, okay? And that's how you extract the slope information of the straight line. Right, so that's your load line. And you have found IBQ and ICQ as well as VCEQ, right? So you can locate those IBQ, VCEQ values in this one. For example, in your KVL, you have found ICQ, right? Say for example, your ICQ is somewhere over here. And corresponding to this point, you have VCEQ. So this is your Q point whose coordinates are VCEQ, ICQ. So this is your ICQ, and this is your VCEQ. Okay, so that completes the load line analysis. Okay. Yeah. So you remember, right? We finding VCEQ. See, this is your VCEQ, and we have also found the ICQ, right? So here, see, ICQ. So ICQ. So this information, when you place it on the load line, you will be able to get the location of the operating point, and by seeing the operating point, you can decide whether the operating point is lying exactly at the center of the load line or not. If, let's say, you want to design an amplifier, and by designing the biasing circuit, if at all you find that operating point is not placed exactly at the center of the load line, instead it is placed, let's say for example it is closer to saturation region, then you may have to revisit your design and you may have to change the resistor values in such a way that the Q point comes at the center of the load line. This is only for amplifier operation. For switching operation, of course, you can select the resistance values in such a way that very high current flows for closed switch operation, and almost zero current flows for open switch equation. So this concludes emitter bias analysis. Okay, so in the next class, let us talk about collector base bias as well as voltage divider bias. Thank you.